Decision Tree in R. Welcome to Decision Tree in R by Simplilearn. My name is Richard Kirshner with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. And we'll be doing part one of a two-part series, Decision Tree followed by Random Forest, because the Decision Tree is part of the Random Forest. What's in it for you? First, we'll cover what is a decision tree, what problems can be solved using decision trees, how does a decision tree work, and then we'll dive into a use case survival prediction in R. So we'll be using the R platform on this one. So what is a decision tree? And here we have kind of a new looking front panel of a car driving down the street, and we have left or right. So you come into an intersection, you got to decide which way to go. Are you going to go left or are you going to go right? Wait or go? So do you go right away? We have a green light, so probably want to go right away after you check for cross traffic and make sure no one is asleep at the wheel or talking on their cell phone. Decision tree is a tree-shaped algorithm used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So another example is we have a shopkeeper. Very nondescript shopkeeper, kind of a little spooky without the eyes. So we have a shopkeeper, and he wants to organize his stall. So I must organize my stall, and he's looking around trying to figure out what the best way to stack all his goods are. And he has some broccoli, some oranges, and some carrots. This is kind of a nice example because we can see where some of the colors and shapes overlap where others don't. And so you can create a tree out of this very easily. You can say, is it colored orange? If it's not, well, it goes into one stack. Well, that happens to be all their broccoli. And if it is colored orange, then it goes into another stack. And you're like, well, that's still kind of chaotic. You know, people are looking at carrots and oranges, a very strange combination to put in a box. So then the next question might be, is it round? And if it is, then yes, you put the oranges into one box. And no, that means it's carrots, we put it in the other box. And you can see that a lot of stuff we do in life easily can fall into like a decision tree. How do you decide something? You know, does it go left? Does it go right? Yes or no? And even with this, we even have a number of different end choices: broccoli, carrots, and oranges. So what kind of problems does this solve? What problems can be solved by using a decision tree? Classification. We're dealing with a classification, identifying to which set an object belongs. And from our example we just looked at, a carrot is orange while broccoli is green. I guess it's nondescript day. It's kind of without the faces. I love it. Because a lot of times when you're looking at data, you really don't want to know what exactly the data is, but you're sorting it. So, you know, like this kind of represents data that you really don't know exactly where it's coming from. Just kind of a fun thing. Regression. Regression is another problem that can be solved. Regression problems have continuous or numerical valued output variables. Example, predicting the profits of a company. So we have two different primary problems we solve for. We solve for classification, is it green or is it orange? And we solve for regression, which is a continual number. So, you know, if you're doing stocks, this would be a dollar value that ranges anywhere from 0 to thousands of dollars. How does a decision tree work? Terms you must know first. So before we dive into the decision tree, let's look at some of the terminology for the decision tree. We have nodes. Each internal node in a decision tree is a test which splits the objects into different categories. And continuing with our vegetable stand example, we have broccoli, no, it's not orange, and oranges and carrots are, and so on. So you can see right there where it splits, that's a node, where the oranges split and the carrots split into each of their own groups. And each one of the splits is a node. The very top node of the decision tree is called the root node. So the very first one we started off where we split it is it colored orange. And you can see that pointed out nice and neatly there. This is a root node at the top. Each external node in a decision tree is called the leaf node. The leaf node is the output. And you can see down here we have our broccoli and we have our carrots and our oranges. Each one of those is a leaf node. So to quickly rehash our terms, we have anywhere there is a split, that's a node. And if it's at the very top of the tree, that's the root node. And if you're at the very bottom of the tree where you have a final answer, that is the leaf node. So you have a root node, a leaf node, and then everything else is just a generic node. So one of the most important terms or concepts that powers a decision tree is entropy. Entropy is a measure of the messiness of your data collection. The messier or more random your data, higher will be the entropy. So we can see here we have broccoli, oranges, and carrots are all mixed together, and it's very chaotic. And you could say this collection has high entropy. And if we sort out the carrots out of here, and I guess just one of the broccoli, I don't know where the other broccoli went, You could say if you have just the oranges and the broccoli, this is a lower entropy. They say this collection has low entropy, but really it's higher and lower. One is higher or lower than the other one. And from entropy, we get information gain. Information is the decrease obtained in entropy by splitting the data set U based on some conditioning. So we have our information 1, which we can there's actual computations. And so we have our E1, which is put in there for our entropy value at the base node or root node. And we have A2, which is a leaf node. And so we can actually calculate, there's calculations for entropy. And we actually look at those two values, the entropy, and we take that, we have E1 is greater than E2. Therefore, the information gain equals E1 minus E2. So here we have another example, and we're actually going to attach some values to this one in just a moment. So we're going to move away from the fruit, and we're going to go to everybody's favorite thing, organizing a child's closet. And here we have a young lady waving at us, "Hi, my cupboard is a mess. I must organize my stuff." And we're going to classify the objects based on their attribute set using a decision tree. We can look at it, we have a shape, a size, and a label, and a number. And I'm going to go ahead and look at the labels, because that's really what's key on this one, is we have a couple balls in here, some books, cards, and blocks. And if you look at that, when you have something that's a ball, it's round, so it's a very different shape. The book, card, and blocks are all rectangular, but the books are a different size. So the books have like a size 6. I guess you think of them as very large. Cards a size 4, so they're not quite as big. And the blocks are little Lego blocks, it looks like, kind of fun to stack on there. And then we can actually quantify this, and we can actually say, hey, we have different numbers. We have 2 balls, 2 books, 1 card, 4 blocks. And we split at each level based on certain conditions on the attributes. So splitting aims at reducing the entropy. And we have a formula, our first actual formula that you'll see happens in the background when we're running these different modules in R. And it looks a little complicated, but we can break that up and simplify that for you. So we see this formula, the negative sum of I of x equals the probability of 1 value of x times the log of 2 probability value of x. The term probability value of x, it's probably easiest to understand if we go ahead and put the numbers in there so you can actually see what we're looking at. And so we plug the numbers in there, we look at the probability of the value of x. Well, if we do the number of balls, there's 2 balls, and the total number of items is 9. So we have a probability of any one object being 2 out of 9. So that's pretty straightforward math. When you look at the numbers, you can actually see that very easily. And so we can calculate our entropy of 2 over 9 times the squared log of 2 over 9 plus 1/9 the log squared of 1 over 9 plus 4 over 9 times the log squared of 4 over 9. So our whole group is the sum of all the entropies. And so when we look at that, we have the entropy of the balls, which is the 2 over 9, rectangles 2 over 9, books 2 over 9, cards 1 over 9, and the blocks 4 over 9. And we can just plug those numbers in there, and we get a value of 1.8282. So what the heck does a module do with that number? Well, now we must find the conditions for our split. Every split must give us the maximum achievable information gain. And so we have our first entropy value, 1.8282, and it turns out when you compare all the different individual entropy values for the balls, for the books, for the cards, for the blocks, rectangles, you find out that the biggest split is going to be in the shape. And it's going to be, our first split will be on the shape that will directly segregate the balls out. So they'll split up a huge group from the other. And so when we compute that, we end up with E2, which is all of our rectangles, and then we have a leaf node, which is the balls. And so with our E2, we see that 1.3784 is much less than the 1.8282. And so our second split will be on the size, as that will directly segregate the books. And so when we do that, we can see that if the size is greater than 5, all the books go to one side, while the cards and the blocks go to the other. And again, we have our E3, which equals 0.716, which is considerably less than 1.3784. So our entropy is dropping each time we do a split. And of course, our third split we look at, and we'll see that we're left with size again, and we split it with 4 and 2. In this case, if it's greater than 3, it's going to be a block. If it's less than 3, it's going to be a card. And at this point, each of our objects is looped into similarity, so they all look the same, and we end up with an entropy of 0. And so you can see as we go down, the entropy continues to get less, And because it hits 0, we can say all our objects are now classified with 100% accuracy. If it was only that easy to clean the kids' closets. And you can see we have a nice drawing that shows you where all the leaf nodes are in this, in which case we have the balls, the books, the blocks, and the cars are part of the leaf node. And the root node is our first split when we have all the object and we're splitting them by rectangle by shape. So we're going to dive into the use case. And in this case, we're going to get a little morbid. There I am behind my desk. That's definitely not me. I don't have that big of a chin. But I do usually have a cup of coffee, and it looks kind of like that. It's sitting next to me on my desk. So the use case is going to be survival prediction in R. And let's implement a classification of data set based on information gain. This is going to use the ID3 algorithm. Don't let that scare you. That's the most common algorithm they use to calculate the decision tree. There's a couple different ways they can calculate the entropy, but the formula is all the same behind it. So ID3 is most common in R. And then we'll be using the RStudio for our interface, for our IDE. So RStudio is free to download. There's the free version. Of course, there's an enterprise version, and there's all kinds of different choices in there. But one of the wonderful things about R is that it's been an open source for a very long time and is very well developed. And it's also very quick and easy to use on a lot of things. So this is going to be in the RStudio IDE. There's some other interfaces, but this is, I would suggest using the RStudio. It's the most common one. And if you remember, I said this is going to be a little morbid because we're talking about how many people survived and died on these ships. So in this case, we have a nice vacation cruise ship going on there, or I'm not sure what that is with the tugboat. So we have a ship, and it had 20 lifeboats. The lifeboats were distributed based on the class, gender, and age of the passengers. We will develop a model that recognizes the relationship between these factors and predicts the survival of a passenger accordingly. So we want to predict whether the person is going to survive or die in a shipwreck. And we'll be using a data set which specifies if a passenger on a ship survived its wreck or not. So we're going to look at this data. And if you open it up into a spreadsheet, and don't forget you can always put a note on the YouTube video down below. And we will be monitoring that, and you can request the data set sent to you or more correspondence. You can also go to www.simplylearn.com and request this data set too. And it's just a simple CSV file we'll send out. And you can see right here we have survived. So 1 indicates a person survived the wreck. 0, they didn't make it. They were under the water. And the luxury class of the cabin, so if they were in, what value is like 1, 2, 3, depending on what luxury class they were. And then we have, this is kind of interesting, how many siblings they had. So it's kind of an interesting added statistic in there. Number of parents on board, and disembark location, so where the destination is. So here we've opened up RStudio. And if this is your first time in RStudio, you'll notice that it opens up standardly in 3 panes. The upper left is for text documents you're bringing in, and then the bottom left is the actual commands as they're processed. And then on the right-hand side, you have your environment set up on there. Now, I've zoomed in with my font a little oversized. In fact, we can even take that up one more size and see if we can get a larger setup view. Here we go. So I've set the font for 18, probably a lot larger than you need to work on a project. And the first thing I'm going to do is on the right-hand panel, we're going to be working with plots. So I'm going to click on the little plot tab up there. And I'm just going to collapse that over to the side for right now. And then I'm going to open up the bottom one. And you'll see on the top, I actually have 2 different tabs. Team in the back was really nice to set up the whole package for what we're working on here. And we'll go through this line by line. And then you'll see as we execute the different lines, they're going to appear down below. So I'll be flipping between these 2 left panels. And let me go backwards just for a second here. We're going to do this part. So let's take a look at the installs. And if you look at the installs, and I'm not going to actually run the installs because I've already run them on my computer. So these are already installed in my R packages, and I don't have to rerun them. We have a number of packages we're bringing into R because that's how R functions. And the first number of packages are all part of our decision tree. So our F selector, our R part, our caret with the dependencies equal true, and our dplyr and our R part plot. Ooh, that's a mouthful. You'll need to import all of these in your setup. And the first one, which is your F selector, computes your chi-squared, your information gain, your entropy. All of those formulas are part of the F selector. So when you bring it in, that's what that package is. The R part is your partitioning of your decision tree. So these are your primary 2 decision tree modules that we're bringing in. The caret is a part for actually splitting apart the data. because we always want to do a test set, a train set. So they built a package caret to kind of handle all those. You'll see caret used in a lot of other machine learning packages when you're doing the R. The dplyr is for mutating your data, so you can sum it, you can classify it, you can filter it. That's all part of the dplyr. And then our part has another piece called plot, and that's for helping us plot the data as we sort out the tree, because the R part creates the tree, but you still want to be able to plot it. And then we come down here and we have some additional tools. We're going to work with a spreadsheet. This is a Microsoft Access spreadsheet, so we're going to use the XLSX package to import it. And you might think that's a little outdated, because I know when I'm doing any new projects, I try to save my data into a comma-separated variable file or something more standardized. But a lot of times you'll end up with these old databases where they're exporting data, and their export comes in an Excel spreadsheet, and guess what? This is a time saver. Instead of opening up the spreadsheet, resaving it as a comma-separated variable file, you can just open it right up in R, which is really nice. And then we have our data tree, which goes right along with displaying the data. So we have our rpart.plot, and we're going to put that into the data tree so we have a nice visual. And finally, you need to install the package CA Tools. And CA Tools is another package used for general manipulation of your data and your vectors. So it also has a split function for training data. I know we have another package for that, but both those packages fit in there as far as the working with the data. So a lot of times you'll see these loaded in there together. And you'll see in a moment we'll import the elementary StatLearn package also, which is very generic, working with data setup as far as statistics and data processing. Now, because my Java setup is a little different because I use the developer package, well, the latest update of the developer package and the R are struggling to see each other. So I need to go ahead and add this in. Chances are you don't need to worry about this. But if you do get an R Java error, you'll need to go ahead and add in a line to set your environment. And I'm just going to set the Java home. I went ahead and looked up the last solid JRE folder, and you'll see under Program Files Java, you can look them all up to make sure it's the JRE and not the JDK. The difference between those is one is a standard executable, that's a JRE folder, that is a folder, not an actual file, and the JDK deals more with developer side on things. And I'm going to go ahead and run this, and if you're in R, you can run these lines individually by holding your control key down and hitting the enter button. So I've now loaded my workspace and set my environment here. And we can actually look and just make sure system.getEnvironment is the opposite one. And I can just look real quick and say, hey, what's my Java home set to? And if I run that, whoops, I forgot to put brackets around it. There we go. And if I do that, you'll see that it's set to the JDK 18025. And again, we're looking at the split screen, and let me just move this up here a little bit, and let me hit the enter key a bunch of times so it comes up on the screen. When I run it, and I'm running it line by line, the run text then appears down here, and this is what's actually being executed. So I could just as easily type it in down here as putting it up here on the top part. And that's just a little bit of RStudio and working with RStudio. So I've shown you the installs. And again, I've already installed it on my computer, so it takes a minute or two to install it. We need to go ahead and then bring those libraries in to work with. So basically, we're going through all the different libraries we're using. Element StatLearn is a standard R library, so it should already be installed. You don't have to install that one. And I can just go right down them, and you'll see as I install them that they show up on the bottom. And every time you go to run a new setup, you need to go ahead and install these, pull the libraries in. You got to tell your RStudio these are the libraries you're using. And you can see right down here that as it executes them, it has all the different things. One of them had like a couple different parts to it, so it loaded the lattice and the ggplot2. Really nothing to worry too much unless you see errors down here. So if you start getting error codes, then you might have to go troubleshoot and find out why it's not installing correctly, or did it install correctly. But it's pretty straightforward. We've covered all the libraries. And again, if you want a copy of this code, simply add a comment down below on the YouTube video, or visit www.simplilearn.com, and they'll be happy to send you a copy of the base code. The next step is we want to go ahead and load the Excel file after setting the working directory. So let's go ahead and set the working directory. SEWWD is the command for that in R. And then this is wherever you have downloaded your data to and your files to. A lot of times if you get the zipped framework sent to you, it will unzip all into one location. And then you got to look that location up and put that in here. A lot of times it automatically sets that for you if you're working in the same directory. In this case, you can see I've pasted in a very lengthy path because I have this as part of my documents, my business docs, and Simplilearn and marketing videos and so on. And I'll go ahead and do the Control Enter and run that. So now my working directory is set. And you can see down below it's executed this on the console down here. And if I open up that working directory, you can see I have a ship XLS file. That's the data we're going to look at. And we looked at that on the slide. You could also open this up, and I will want to go ahead and open it up with a notepad. By default, it'll open up as a spreadsheet. Oh, it is an Excel file, so I'd have to open it up as an actual spreadsheet. Wasn't thinking that one through. This is one of the problems with saving stuff as a proprietary ship file, even as something as widely used as Microsoft Excel spreadsheet. But when we open up the spreadsheet, you can see here the same data we looked at before. That's what's coming up in this file. And so I take this file, we can go ahead and let's create a variable. We'll call it add. And we're going to assign it. That's what the lesser than dash means if you've never used R before. And we're just going to assign it a ship XLS. And then I'll do my Control Enter and you'll see it run down here. Ship. Add is assigned ship.xls, our Excel spreadsheet on there. And then let's have another variable. We'll call it df for data frame. And we're going to assign this read XLSX. And that's from the library SLXX that we just imported. And we want to read the file add, because we just created that variable with the ship.xls. And I didn't catch this right away, but you'll see when we open it up in a spreadsheet, it might be hard to see in your video screen, it has the first sheet is called ship 1. So this data is on the page ship 1 in the Excel spreadsheet. And we got to make sure that we tell the reader to look for that. And so we can simply do that in our command line. Sheet name equals, and it was ship 1 on there. So we go ahead and hit the Control Enter and run this line, and it brings it down below and executes it. It's now reading in that data from that spreadsheet. That's what's going on. And it takes it just a moment to go ahead and read it in. And then with any data processing, we need to select the meaningful columns for the prediction. So this is important that we sort through our data and set it correctly so that whatever we're feeding it into can read it correctly. We can do this with df. We're going to reassign it, and we're going to select, and from there we're going to select df as our main data frame going in, and then list the columns that we want. And if we look at the data, we have survived, we have a class, we have a name, sex and age, and then there's siblings and parents. We really don't want to know the name because we don't need the name to run this on here. And then we got to decide which one of these we want to work with. And the guys in the back played with the data a little bit, and they came up with the following columns. Survived, which we need definitely, because that's what we're actually trying to figure out is whether we're going to survive or not. What class which class of the boat they're riding in, whether first class, second class. Sex and age. And we went ahead and dropped the rest of them, at least for this example. And so I can go ahead and do my Control Enter, and you'll see it execute down below. And now df equals these 3 columns, or 4 columns. Plus our answer is one of those. So I always think of it as 3 columns plus 1, but it is 4 columns. And then for the next step, we want to make sure the data is in the right format. So again, I'm going to reassign the df, and we're going to mutate the data. And that means we're going to take each one of these columns, and we're going to let it know what kind of data that is. So our first one is we got to put the database in, or the data frame in there, df. And then we want to go ahead and do survived equals a factor of survived. So this is a yes, no. It's letting us know that this is a 0 or a 1 on here. And then for the class and the age, those are as numeric. There's other ways to process class since it is a very restricted number on there, but for this we're just going to do it as a numeric value. Same thing with age. And you see we didn't do anything with sex. We're just going to leave that as male or female. And that's fine for this because it'll pick up on that when we run the decision tree. And we'll do our control enter. So now I've assigned the new df, and you can see it comes down below as we run it on there. So this is now loaded, and df now is a mutated data frame that we started with, and we've set it up with our specific columns we want to work with. In this case, survived, class, sex, and age. And we've formatted 3 of those columns to a new setup. So one of them is factor. That's what we use for survive. So it knows it's a 0 and 1. And then we switched class and age to make sure that it knows that those are numeric values. Now that we have our data formatted, we need to go ahead and split the data into a training and testing data set. And by now, if you've done any of our other machine learning tutorials, you know this is standard. You need to have your data that we train it with, and then you got to make sure it works on data that it hasn't trained on. So we'll go ahead and do the splitting. Let's take a look and see what that looks like. And when you're dealing with splitting the data, we're doing a little randomness, so we'll just go ahead and set the seed to 1, 2, 3. You can set that to whatever number you want. That's just setting the random variable seed. And we'll go ahead and hit enter on there. And to do this, we're going to create sample, and we're going to go equals sample.split. So we're splitting up the data. This is actually creating a whole new column, trues and falses, and it's all stored in sample. And we want our data frame, and we use a $sign to denote that we're going to be working with one of the different columns. A nice thing you can do in R, and it actually shows my survived. So df survived. And then our split ratio, I wanted to add a period in there, which it doesn't have. Our split ratio is going to be equal to, and we'll do 0.70. So we're going to take 70% of the data of those that have survived, and we're going to just randomly select which one of those we're going to use for training and which one we're going to use for testing it out later. And we'll hit our enter and load that sample in there. And then we'll go ahead and create our train and our test data set. So I'm going to set train equal to, and this is where it kind of gets interesting because we're going to do subset, and then we're going to do a subset of our df where sample, and then we're going to use equals, since this is a logic gate. So wherever it sets sample equal to true, we're going to use that line in df. And this is, of course, R, so it's all capitalized for true. So here's our trained data frame we're creating. So when I execute this and it shows up down below, it goes up and says, hey, this sample created a whole bunch of trues and false. And we're going to take those trues and falses, and wherever we've created a true, which is 70% of the data randomly selected, that's what we're going to train the data with. And then we need our test set, and that's a subset, just the same thing we just did. And we need our data frame, and this is where the sample equals false. And again, when I hit Control Enter, it goes down this line of code and it runs it down here in our terminal window. So now we've nicely split our data up. We have our training data set and our test data set. And this is, of course, where we get to the point of what we're actually trying to do, which is create our decision tree. And we're going to do that by training the decision tree as a classifier. This always gets me. You spend all this work sorting through the data, reformatting it, in this case mutating it and filtering it, and creating a train set and a test set. And so we're going to go ahead and create our tree, and we're going to assign to it the R part. That's the module we imported. And for the R part, we need to go ahead and do what's called a survived, and this is kind of a little complicated to look at, so let's just take a quick look at this, and I'm going to go backward on it. The first part is we're importing the data, so data equals train. And then what we want to know is who survived. So The first part we put in here is the column we're looking for is survived. And you'll see that we have added the squiggly mark in the period because we're looking just for this prediction. We just want to know who survived on these boats for programming our decision tree. And I'll go ahead and hit Control Enter. And we've now created the tree. That tree with all those values is now in there. And if you remember from before, we've taken from when we did the closet full of clutter, we've done the same thing where we have our entropy, and that one line computes the entropy and the increase in information. And it brings entropy down to 0. So it's the same thing, but instead of applying it here as we did visually to the closet, it's now applied it to the data on the ship. It's now looked at the survival of 0 or 1 based on female, male, what age they are, where the best split of the age is, and what class they were in. You can see we have first class. If we go down there, I think there's third, second. So I guess it's class 1, 2, and 3. But you can see that's how it's split it up. So it's used these different variables to minimize the entropy and maximize the information gain. And that's all done in that one line of code. Boy, we worked on all that theory, and computer does it for you in one line of code. It's important to understand the theory behind it so you know what's happening. Because as they make changes to these, or if you add special settings on it, you have to know what they're doing. But in this case, you can see that once we get it formatted, the computer does all the heavy lifting for us. And it never ceases to amaze me just how advanced machine learning has become these days, and how easy it is for people to get into it and learn the basic setups and be able to compute your different machine learning models. Once we've computed our decision tree and we built it on there, we want to go ahead and start doing predictions with it. And what are we going to predict? Well, you remember that we created our data with the train and test. So we have our training data, which we programmed the tree for. Now we want to see what it does with the test data. So let's see what that looks like. And we can wrap that into tree.survived.predicted. We'll assign that to our prediction. And this is nice because we have the command predict from one of the modules, the rpart module that we brought in. And I can simply put in here that we're going to use the tree. We have our test data and type. And this happens to be classification or class. And this would also be if you were to distribute this tree. You could save the tree and send it someplace else to be used on new data. This would be the command line you would use to predict on here. Predict, you have your tree saved, you have whatever data you're putting through, and you let it know it's doing a classification on the tree. And we'll go ahead and run that. So now that's loaded up. And now that we've gone through, we've trained our tree, we run a prediction on our test data. Remember, the tree had never seen the test data till now. So we've already built the tree and we're just testing it out. And to do that, we're going to use a confusion matrix for evaluating the model. And let's see what that looks like. And that is simply confusion matrix. So once we have the confusion matrix, which came in from our caret, we need to compare the two different pieces of data. And the first one's going to be the value we generated up here. We have tree.survived.predicted. So I'm just going to copy that and paste it down here. And then the second one is the tree. We're comparing that to, let's see, survived. And it's not the tree. It's easy to get confused sometimes when you're moving these things around. We're going to compare it to test, the test group of data, specifically the survived column. And let's go ahead and run this and see what that looks like. And so let's go ahead and scroll up a little bit here to where it first executed the confusion matrix. And the most important part of this is that we have our prediction and our reference. And so 0 means they didn't survive, 1 means they survived. We had our prediction on here versus the actual. And that's what these two columns mean. And so when you read this little chart, we have 0, 0. So both the prediction and the actual reference said we agreed on 218 values for people who did not survive. A little grim there for data. Remember I talking about this is morbid data, talking about death rates of people on boats. And it says that they both agreed on 93. So 93 of them where we predicted the value that they would survive, and the reference came up the same. Likewise,
the predicted, where it predicted 1, and the reference said, no, these people didn't survive, well, our prediction got 25 wrong. And where it says they didn't survive, and they actually did, it got 57 wrong. And we can come on down with the confusion matrix, and we can look at the accuracy. It comes up with the 0.7913 or 95% CI. So yeah, you're looking at pretty high accuracy. Information ratio, p-value. When you're in statistics, the p-value is one of the things we look at. Remember that there are certain values, if it's over 0.95, it's considered highly valuable variable. 0.5 means maybe, anything less than that means it's probably not connected. You have to look up the p-value a little bit more on that. And then they just have more information down here, which you can go through and But the important part is that we have a very high accuracy. That's what we're looking at. This is a very accurate model. And again, always remember the domain you're working with. Certainly this is an example, and this is a good little piece of data you can play with. But if I was, say, betting money, and my accuracy came up as 79% or over 95% CI, I'd be like, yes, let's bet on that. That's a good bet. But if I was betting on a life or death situation, I might kind of rethink that a little bit if it's going to affect my life that way. You can also look at this as if you're trying to figure out where the boats go in this particular example and where to put the lifeboats. That's actually pretty good. Be able to say, hey, we can increase the chances of people surviving this accident by putting the lifeboats in the appropriate places. And then, this is always fun. Let's visualize the decision tree. One of the cool things you can do inside of R real easily. And if you remember, one of the modules we brought in has a rpart.plot. We're going to take that and we're going to dump that into the PRP for the tree. And we'll just go ahead and hit enter. And this is fun. Let me move this over so you can get a nice view. You can see how it actually split it up. And let me just rerun that again. Now that I expanded the right, you'll see right here where one of the biggest splits was whether the person was male or female. I didn't know that was probably one of the biggest breaks as far as lowering the entropy and increasing the information gain. And then once sex is male, it came down here and it said you're not going to survive. I guess the men were throwing themselves overboard on the boat. I don't know. Maybe they're being very gallant and letting the women and children survive, which is what I hope that means. So once you know that it's not a male and it's a female passenger, if you were in class 3 or above, you had a high chance of surviving. If you were less in class 3, class 1 or 2, then it was based on age. And so you can see where age was greater than 19. So anybody over 19 had a high chance of surviving, and then if they were, or less than 19, I'm sorry, if the age was, a little confusing on that one. But if the age was one side of 19, they probably survived. If not, then it said, hey, if your age is less than 60, you probably survived, and if not, people who are older probably didn't make it out of the boat in time. So elderly have a much higher risk, which you would expect. You'd expect that to be the case, that elderly would have a hard time getting off into the lifeboats. And they would probably step aside for the younger generation. I know I would. So that might be more of a social norm statistic as opposed to a survival rate. Let's go ahead and put this back on over here and see what else we can do with this data. If you're working with the shareholders, it's good to have a lot of tools as far as how to display. They'll want to see this number here where you say, hey, this is what the confusion matrix looks like, and we got a 0.79 accuracy. That would be like the number one thing you would talk to the shareholders about. Other data scientists care about the p-value and the information rate and information like that. But this is really the core right here. This is how much data, and this also shows them how much data was looked at. So you can actually just add these numbers together and you can see how many different people were in this particular data set, or how many lines in the data set. But we go ahead and visualize the 2D decision boundaries. And let's take a look at that. That's kind of fun. It's a little bit more complicated, so I'm not going to go into it in too much detail today. Now, the guys in the back put this code together for me, which is great. So I'm just going to paste that in, because like I said, we're not going to go into it in too much detail. I want to just show you that there's some other ways to display the data that is not just this nice little tree over here, which gives us a little bit more maybe view of what's going on. As you dig deeper into data, that becomes very important. It might not be something so simple where you can look at, in this case, 1, 2, 3, 4 nodes. So they have 4 major nodes that they split the data in. So when we're looking at this, we're going to go ahead and create a set test equal to test, comma, C241. We're just assigning color column to go with the data, okay? That's what that is. And then we're going to take set and have it equal to test. And we'll do x1, and we're going to set that equal to minimum set of 1 minus 1, max set of 1 plus 1 by equals 0.01. They had to play with these numbers a little bit to get this to look right. So we're creating a sequence on here from the set we created, so our test set. And then x2 is also creating a sequence based on different values. And then we're going to put that all into a grid. So let's go ahead and run that through all the way down to the grid. And they'll make a little more sense when we add the column names to the grid, okay? So we'll set our test, we'll create our x1 sequence and our x2 sequence. Remember, a sequence is just like, in this case, starting with 0.1, it's like 0.01, 0.02, 0.03, 0.04. So we're going to create a grid with all these values separated by 0.01. So that's all we're doing right now. And let's go ahead and set that up. There's our grid. And then we want to go ahead and create some column names. And for our grid set, we're going to have our C class and age. So we're just doing the class and the age on here. Remember, we did sex also before, so it's just class and age on this chart that we're pulling out. And we're going to create a Y grid, and the Y grid is going to equal tree survived predicted. Okay, so here's our Y grid and our predicted values on there. Now we're actually going to do something. We're going to plot, and we're going to plot the Y grid. Oops, hold on, let me see what's in here. And let me go ahead and just run the plot. It's got to be the there we go. So let's take a look at this and see if we can make a little sense of this code and what's going on here, because there's a couple of things going on. What we've done is we've plotted a decision tree classification data set. We've done our plot, and we have our set. So our set's equal to our test data. And then we have our main. We went ahead and give it a name, decision tree. And then we have our xlab and our xlimit, and we've set those up as class with our ylab equals age, and our xlimit equals range x1 comma ylimit equals range of x2. And when you look over here, you can see that we have age on the left and class on the bottom. And so based on age and class, and so once we put in this nice graph here, we want to go ahead and add our contours and our points. So let's go ahead and run that, and I'm going to run all three of these so we can see all the colors come in on the graph. And this is actually going to take a little bit, because remember, you can make it go a little faster by changing a couple of the notes up here. When we did 0.01 from the min to max, by changing that to 0.1 or other values, you can actually, it'll run a little quicker. And we're going to create a nice little decision tree classification test set just to see what that looks like and how that data displays. Now, that was taking so long to run with 0.01, I went ahead and just did a 0.1. So instead of filling the whole page with different colors for a really pretty view, now I just have these different colored lines coming across. It gives us another model that we can show for whoever you're working with, in this case, your shareholders of the company or the individuals who you're posting to the web for. And you can see where we have the green and the red, and we've set those up to identify from the decision who's going to make it and who's not based on age and class. Now, my favorite one on this, and I'm going to go back and just highlight this really quick, was, let me just rerun that, go back to PRP tree where we display the tree. And that's where we split it in part, because this information gives us some keys that we can then use in other models. So it's good to know that sometimes what you're taking comes out, and maybe you create a bucket for people under 19, between 19 and 60, and over 60, and different things like that, so you can actually put people in buckets in a class age split. Just a quick note on there. Again, lots of different things from which you can display the data, and you can see how we use the decision tree to figure out chances of somebody surviving based on their class and their age. So let's go ahead and wrap it up. We had a good time here. And let's look at the key takeaways. We went over what is a decision tree. Of course, we had our faceless vegetable booth guy who's got his, I guess he's fruit and vegetables, who has his oranges and carrots and broccoli, which he split up into different groups. Then we went over the problem solved using decision tree, where we discuss both classification and regression, because you can also do regression models. We went over terms to know. Very important to remember entropy, or how chaotic the system is. We discussed information gain. And of course we covered the nodes, including the root nodes and the leaf nodes. And then we went over how the decision tree works. We looked at the actual math behind it and how it computes entropy and how it keeps splitting it until the entropy is 0 or as low as it can get. And finally we went into our R programming, and we wrote an actual script in R to use the decision tree for survivors on a boat. And we covered both formatting the data and setting it to predict the survivors, to train and predict. And we also determined the accuracy of the prediction and looked at a number of ways we can display that to share that information with other people. So that's going to wrap it up for today. Thank you for joining us. For more information, visit www.simplylearn.com. Again, my name is Richard Kirshner with the Simplilearn team. Get certified, get ahead. Do feel free to add any comments below, or questions or requests for data sets or code sets. Or you can go to www.simplylearn.com and send a note there. Again, thank you for joining us today.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.